is Genevive LaLonde, and I'm a senior support engineer at SingleStore. And I'm going to be talking about query performance tuning. So first we'll talk about just query processing in general, give some background information. And this includes the two stages of query optimization, which is creating a query plan to run, and query execution, which is actually running that plan. And it's important to remember that SingleStore is a distributed database. So we've got aggregators and we've got leaves. And both of those types, both of those roles are going to be processing their own queries, and they each hold their own plancache. So the way that we generate a query plan is that the app is going to send a query to the aggregator, maybe something like select star from orders and filter it on ID = 7. And then that aggregator in turn is going to send out distributed queries to the leaves, and it sends them out as the distributed user. So that might be something like select star from still orders, but we're going to be rewriting it a little bit. So instead of just saying not even indicating the database at all, here we're indicating the database and the partition that it's going to be on, partition 21. And then we would still be filtering on ID = 7. This is a simplified form, but it would be something like that. So keep in mind that the aggregator has its own query plan, which is going to be more of a complex plan, and then it sends out simplified forms to the leaves, to each of the partitions. And it can send out several leaf queries for each of its own application queries. So let's take a look at how that happens on just one individual node with one plancache. So this is going to form a few steps. When we get that query, either from the application or from the aggregator, the first step that we're going to do is rewrite it. We'll take some things that are implicit, like a select star, and we'll make it explicit. We'll rewrite it and add each of the actual columns that we're selecting, be really explicit about which database they're coming from, things like that. We're also going to parameterize any parameters. So here we're filtering on 7. Well, if we didn't have to consider that it always is 7, maybe we might filter on 217. But we could really use the same query plan because it's the same query shape. So we'll go ahead and parameterize that and replace it with a wildcard instead. That means that we can reuse the same query without having to optimize it again, which eliminates a lot of the cost of the first run of a query. So the next step, now we've got our query text that is very understandable for the engine. What we're going to do is create a hash of it so that we can uniquely identify it. This is also called an activity name or a plan hash. And it includes some information that's recognizable about the query itself. This was a select. You can see it operates on the table orders. If it were joined with other tables, it would have et al in here. And then there's a hash at the very end. And this is a truncated form of the hash. It's actually much longer. And this represents anything that could make this query be different. So it's the query text, including any white space or capitalization. Those are unique. Any variables, the memSQL version itself, any hints, any options, anything that could modify this query will be included and hashed in here so that you know that this is a unique identifier for that query plan. So once we've got that, we're going to use that hash and check and see if it exists already. Do we have that in the in-memory plan cache? Do we have it? If not, then we'll go ahead and check on disk. Do we have those files stored on disk? If so, we'll pull them into memory and keep them in the in-memory plan cache. In this case, since this is the first run of a query, we don't have it in either place. That means that we need to optimize a new plan. This is going to use mostly CPU, so I put a little CPU over here. It also uses memory. And when it's optimizing this, it's going to be considering what's the best join order, what's the best algorithm operator, and it uses statistical information about your tables to help inform those decisions so that it generates a better plan. This is the cost-based optimizer, which we use as of version 6.0. The next step is that we generate a memSQL bytecode. You can even see this as its own file, .mbc, stored on disk. And the beauty about SingleStore as of version 6.7 is that we support interpreted mode. So what we do, as I said, the first run of the query can be really expensive because we're compiling that plan. We're generating the code and compiling the files to disk. So that can take a lot of time. But really, once we have the byte code, we can go ahead and start executing. Instead of waiting for the compilation and running from the compiled plan, we can interpret the byte code. So we go ahead and do those two things at the same time. While we're still compiling the plan to disk, we'll start executing the query from the byte code. And if any individual operators finish compiling before they're interpreted, we'll just switch over to the compiled version of that operator instead, because it's probably going to be a lot faster. If you were to rank the fastest way to run queries, the fastest one is going to be running previously compiled code. Second fastest is probably going to be running the interpreted mode. And the slowest form is if you had to wait for the compile and then executed from the code that you compiled. So it's a nice benefit that we can just interpret it right away so we don't have to wait so long. All right, so we finished executing our query, and we're going to go ahead and cache that plan in memory. By default, it's cached for 12 hours in memory, but you can adjust that to longer or shorter. We'll talk about that later. After that, it will continue to live on disk for 2 weeks. So the files will still be on disk, but we'll pull it out of memory after it expires. And anytime in those 2 weeks, if that query is run again, if the same plan is used, then it will be pulled back into memory and those counters will start over. So if you regularly run a query at least once every 2 weeks with the default values, then we will never get rid of the plan. We'll just keep reusing it. And that's nice so that you don't have to worry about recompiling a plan over and over again. However, if you do have one-off queries that you just run it once and then you never run it again, you know that within 2 weeks, or after 2 weeks, we'll go ahead and delete that file and you don't have to take any manual actions to make that happen. So we don't consume too much disk for all of those cached plans. All right, I mentioned statistical information before. This is how our optimizer makes informed decisions. Well, there are 3 different types of stats that we can collect. And some of these can be collected automatically, which we'll discuss later. But for now, let's just look at the types. So the first type is a cardinality autostat. A cardinality stat. So a cardinality is a count of distinct values. So for example, if these are 2 columns, the one where all of the values are the same, that's very, very low cardinality. That's about as low as you can get. Whereas if all of the values are unique, that's about as high as you can get. So when we store a distinct count of each of those values, we can have an understanding about the distribution of values and the cardinality of them in those columns. Next, let's take a look at histograms, which are also called range stats. These are the minimum and maximum values that you have. So in this case, 8 would be the minimum for this column, and 85, here it is, that is the maximum. So for row store tables, that is stored per partition, but for column store, since the minimum unit of storage is a column store segment, we store that per segment in the metadata. And this is used in segment elimination, which you might hear about, where we can determine from that metadata whether we even need to scan that segment when we're doing query execution, or if we can just eliminate it by using the metadata before even accessing the data itself. Finally, let's take a look at sampling. So sampling is performed during data ingestion or write. And what we do is we take a statistically significant sample of that data, and we store it internally in a sampling table. So here we've taken 4 different rows from this table here, and we can use this for filter selectivity. Histograms and sampling stats are also, they're both really good for filter selectivity. Because in this case, if we were filtering on, say, 112, we could tell that we don't have that value in this partition, so we don't need to look at it. For this one here, if we were filtering on 12, x greater than 12, just looking at our sampling table, we can tell that meets most of our samples, so it's probably going to meet most of our rows in our table. It's not very selective, and that's true of the table here. And this percentage that we store in this sampling table is scoped for how big your table is. So I'm going to represent these with these little images. Cardinality is a count of distinct values. So here is the count from Sesame Street. Histogram is going to be your min and max. And sampling is, it's kind of a small table that we store in metadata. So now let's look at how we collect them. Mostly your stats are going to be collected automatically, so you don't need to think about it. And there's a bunch of different ways that you can collect stats. So incremental is going to be collecting cardinality stats as metadata at the time that you're creating column store segments. As opposed to if it was collected periodically, then at a certain interval, we would check to see how many rows have been inserted to a table. And if it exceeds a particular threshold, then we'll go ahead and collect those stats periodically. Same stats, just collected at a different time period. Or you could set it to off. For histograms, they are not created on most columns, and we have some, you can adjust that behavior. You could either have them create automatically, which means that if two queries would have benefited from a histogram on a particular column, then we'll go ahead and create it. And queries that benefit from histograms are ones that, for example, filter on a column. And you can track these. There's an internal table in the information schema, which shows you which columns are under consideration. Alternatively, if you don't want a lot of histograms being created because they can consume some memory, then you can say, okay, don't make new ones, but for any ones that I already have, just keep them up to date. And these will be updated on the same schedule as the periodic autostats. Or you can just set them to off. And then finally, sampling stats. These are collected, like I was saying, during the writing of data to tables, and you can either set it to on or off. But specifically, different types of tables have different default values. So for column store tables, as you can expect, incremental stats are designed for column store segments. So that's the default here. But if you prefer, you can set it to periodic instead. The default for histograms is that we're going to create those automatically if we see that they would be useful. And for sampling stats, that is also set to on by default. For row store tables, it's a little different. We don't have column store segments for row store tables, so we can't have incremental stats. So periodic is the default. We still create histograms by default. And then for row store tables, you actually can't disable sampling stats. We created them sooner with a different methodology, and so they're just inherent to the table itself, so they can't be disabled. Now, all of that was automatic behavior, and you can control that, like I said, by adjusting the settings or disabling them, or even just disabling them globally for the entire node. But you can also manually collect stats by running the command analyze table name. And what this does is for cardinality stats, it will just collect those cardinality stats, the same as if a periodic stat was executing on that interval. For histogram, that will go ahead and update any histograms that you currently have. You can also use a slightly different command, analyze table name, column, and then you list the column name and tell it enable, and that will create a histogram on the columns that you indicate. Or you can tell it column and disable, and you can use that to disable histograms that you currently have. For sampling stats, that's only collected when there's a write happening, so we don't collect any stats for it with analyze. But analyze has this other behavior that you don't really get anywhere else. It's called plan invalidation. So what this does is it checks query plans that we currently have, and it compares the stats that they had when they were generated, all those estimates, with the stats that we currently have. And if there's difference by a factor of 2, so that means either a table doubled in size or reduced by half, then at that point we'll say that plan might not be as good anymore because the data is highly different. And so because of that, we'll mark this as invalid. And the next time that that query runs, we'll go ahead and generate a new plan for it at that time. So this happens when you manually run analyze. This doesn't happen automatically. So let's take a deeper look at plan invalidation, because we've got some plan caching like I mentioned before. Plan expiration minutes is the variable that controls how long we store the plan in the memory plan cache. So that is 720 minutes, which is 12 hours, half a day. So it'll stay in memory for 12 hours, and if you run it again, it'll just reset that timer and stay in memory for longer. If it Otherwise, if 12 hours pass and you don't run it again, then it will expire from memory, but the files still live on disk. So at that point, say that it's been 24 hours, and then you run it again, you'll pull the plan from disk into memory, and this timer will restart. But if it was run once and then 2 weeks pass, or 21,060 minutes, then at that point, it has reached its disk plan expiration, and the files will be deleted from disk. That occurs at the next run of the plan garbage collector. If you run the query again at that point, say it's been 15 days since the last time that you ran this query, then we'll have to go ahead and create the plan again. And like I said, anytime that you run the query, those timers will be reset. Let's take a look at the drop command. So you can either do drop all from plancache, or you can drop plan ID from plancache and indicate a particular plan ID. And the way that you find that plan ID is that you can filter on the info scheme of plancache, filter it on the query text to identify the query that you're looking for, and you can pull the ID out of it and run it with that. Please note, in version 7.1 and below, the plan already had to be in the memory plan cache. Otherwise, this command would not work on it. It would only drop it from memory, but would leave it on disk. But as of version 7.1 and above, this will go ahead and operate on them both. And then the final methodology of invalidating plans, getting rid of old plans, is analyze. So analyze, like I said, is going to invalidate it if it was generated when stats were different. Excuse me. So I want to point out a couple of differences between these. So analyze is manual, drop is manual, plan expiration is automatic. The drop is going to be invalidating the plan. Also, analyze is only going to be invalidating the plan, but they don't actually delete the files. The only way that the files are deleted is once they have reached their disk expiration time. We won't use it. It's been marked invalid. We won't use it, but the files will still live on disk, and they'll only be deleted once they would have expired from disk after 2 weeks. So if you are seeing a lot of disk usage, you might consider reducing that variable, disk plan expiration minutes. And that will mean that plan files don't stay on disk for as long between their usages, and it will reduce the amount of disk that can be used for plan caching. The same is true of plan expiration minutes. If you see a lot of memory being used for your plan cache, you can reduce this. And that will expire from disk, but they'll still be, that'll expire from memory, but they'll still be on disk until this expiration passes. So plan expiration is the way that the files are deleted. And then the difference about analyze is that this is really the only method that you can use to refresh a plan if it's used pretty frequently. Because again, if you use it at least once every 2 weeks, it will never expire automatically. Even if the tables have changed significantly, we will continue to use that same plan. So if you want to refresh your plan based on current data, make sure that you analyze. And this is going into that a little bit more deeply, because I know a lot of people tend to have questions about that. The main thing is, why did we decide to do that? That was a very specific decision. And it's because we want to offer the guarantee that if you have a good plan that you like, nothing's going to happen to it. It will continue to be used, and nothing automatic is going to get rid of it. The only automatic behavior is plan expiration, and that only happens on queries that are maybe one-off or that don't get run for 2 weeks. So they're old and not used. And we will have some future work in this area as well to look at more ways that we can determine whether a plan that is used regularly is still good, still adheres to current stats, and do some background work to check that. So the trade-off of offering this guarantee is that we'll keep using our good plans, but we'll also keep using our bad plans. So a plan can go bad if the stats that it was created on diverge from the current stats. The more writes that you have to a table, the more chance that that plan may no longer be good. And it requires a manual action. Either you drop that plan or you run analyze in order to fix that problem. Yeah, and so if there's a high rate of data turnover and you're not analyzing, then you might start to get bad plans. The thing to watch out for is if a plan used to be good and slowly over time it got worse and worse. If that happens, consider analyzing. And so a good recommendation is to just add analyze to your workload. We used to recommend analyzing very frequently in order to collect statistical information. And it's not necessary anymore for that, but you still need it to clear out and refresh these plans, which are run regularly, but need to be refreshed. So you could consider adding it after writes to your table, like ingest, insert, delete, update. After those are committed, you could analyze the table. Or you could just do it maybe once a week at a low traffic time. But there's one exception. The only table that you don't want to analyze frequently is tables that are frequently empty. For example, a queue-type table, something that you'll load data to and then you do something on it and then you clear that table back out. The reason for this is based on our optimizer. I mentioned before that we have a cost-based optimizer as of version 6.0. Before that, we used a rules-based optimizer. And this was pretty good. It would make some general decisions about the join order and other things. But the cost-based optimizer is actually looking at your data and it's figuring out the statistical information about your table like we talked about before. So it makes informed decisions for your data set. Whereas the rules-based optimizer is more generic. So the cost-based optimizer usually makes better decisions. But if a table is empty, the cost of running any operation on it is going to be 0. So it doesn't really make sense to consider its cost because it will always be 0. So in that case, we don't use the cost-based optimizer, we use the rules-based one. The thing is, a table might not actually be empty, but the stats could say it is empty. So if you just run analyze maybe once a month, it's possible that that table got some values added to it in the meantime, but you didn't analyze again. Autostat should be able to update this, but you need to analyze to clear out those plans. So it's possible that you generated plans when stats were empty, and those plans will be used when the table is not empty and the plan won't be good. So it's kind of a tough situation, a lot of moving parts here, but the way to fix this is just to override this behavior manually. What you do is you populate that table with some data, you analyze it then. So you've collected the stats say it's not empty. And then at that point, disable the auto stats. We don't want that information to change and reflect that it's empty at any point. And don't analyze it again until you mean to. So what this does is it ensures that the stats always reflect that the table is not empty, and we'll always use the cost-based optimizer. It's a bit of a trade-off. So we don't have the most recent stats. Maybe we won't generate a very good plan, but the cost-based optimizer will generate a better plan than the rules-based optimizer. So we want to make sure that it's used instead. And generally, a queue-type table tends to be smaller, so it's okay if the stats are slightly divergent from what they actually are. It won't have as much of an impact as if you use the rules-based optimizer.